are here to talk about.
Trying to think who I need to unmute or to mute here. Okay, Carrie, you're on.
Okay, so shall I start?
Yes, please.
All right, so good afternoon and maybe good evening. My name is Carrie Chen. I'm from Intel Taiwan. And here with me today is Levin Ko, who is hardware architect from Foxconn, China. And also we should have another one. Jay is from Baidu, who is system architect, but he is currently in Beijing because the China OCP is also up on this week. All right, so I will be leading the presentation today, and Levin will be help. We both responsible for any technical Q&A after that. So let's get started. Our topic today: a passive immersion cooling solution for outdoor edge server. So the passive immersion cooling will be our keyword here, and also outdoor environment. So let's go through the agenda today. Let me walk you through why immersion cooling for high performance edge server system, and also we will talk about a typical high performance edge server, what the configuration looks like, and also for today's primary part discussion here is what we will share the design consideration from our test finding up to today's early engineering sample is actually up and running. And also a single phase immersion cooling system architecture and our validation result, we can share what we have up to today. And also the engineering practice key learnings that we are open and share with this committee and everyone here. And we will wrap up with the call for action. All right, so let's take a look at why immersion cooling for high performance edge server is a trend we observe, and also we heard a lot of our end customer is their applications is required such of the design for the feature compliant. So we know the immersion application is multi-phase high performance server moves out of data center and offering service at the edge, and also the multi IoT devices, the fleet management calls also for high performance edge server. And we found the conventional air cooling solutions are challenged and probably more and more unable to fix this thermal issue by high density performance server in data center. And we found it should be and definitely were even worse situation in edge environment, the outdoor, when we deploy that. So the outdoor edge server needs to operate in a harsh environments proximity, and most of the spec requirement will be minus 24 degree to 55 degree temperature range. And the humidity is around 5 to 95%, and which calls out the industry standardized on IP65 and to the 67 compliant. So we think the immersion solution should be the perfect solution to meet this goal. So that's for this background. So let's move to the next. Here we were just trying to bring up an example of a typical system config on what we call as high performance edge server. So in here, an example is we use Intel Xeon scalable processor gold segment CPUs, and at least, here we say at least 2 high performance AI accelerators and up to 55 degree ambient temperature is required, and as well as IP65 at least here. So in here, the 55-degree ambient temperatures, we are still testing in progress, and we will continue to share our validation result when it becomes available. All right, so in here, we are going to enter a main discussion for our today's topic as our design consideration, what we found from our past finding and up to today to this early engineering sample is actually the functional one. So we think firstly, most importantly, if we want our product to be commercialized, the cost is the first consideration that we need to be very careful during our design. So we think two-phase immersion has relatively high loss rate and consume bigger space when we actually need to deploy outside. And also we found the cost efficient liquid is important, which will be the main cost, design cost, and also which may help us to do the feasibility for commercial products, right? So we think and we found the hydrocarbons and it also called synthetic oil, right? It's much lower cost and also more environmental friendly compared to fluorocarbons. So that's our finding. And this one is how we select liquid, what is the key parameters that we need to select our the liquids for validation. So firstly, in the choice of liquid, we consider the electric strength is the most important parameter for any liquid that is used for immersion, because we have to consider to avoid any electric shortage. So this is very important and very critical one. And since the system is in the form of natural convection, the viscosity coefficient is also an important parameter. So both are also important, but I think this can be a guidance or a reference for the liquid solution. And when the liquid is get heated, the density will change. So choosing a liquid with a low viscosity efficient coefficient will produce a better flow effect. So which means a better heat transport effect here. And in this case, right, what we're gonna share is we select a liquid called PaO2 as to be our first engineering liquid validation. And this is because we think is we think the solution cost will be only about approximately 5% of fluorocarbons compared to the current fluorocarbon solution. All right. And the next we will talk about what we found and we should consider for your design on the system thermal. So since the system, we know we will propose a place outside, outdoor, right? In the outdoor situation, a passive immersion cooling solution is to reduce the use of moving parts. That's why we emphasize here, like the fans, the pumps, to reduce the chance of maintenance, which is really necessary for the real deployment. And the heat dissipation inside the system here, we think will be transferred to the external environment by heat exchangers on chassis wall. We will have a real prototype chassis in later by natural convection. So the internal, you see the internal flow field design of a passive immersion cooling solution is based on the concept of thermal buoyancy. Right, so we will recommend to place high power components below to increase the overall heat transfer efficiency. So we recommend that high power or low temperature limit components, they need to be placed at the bottom. And the lower power or higher temperature limit components, and we recommend need to be put at the top. So that's what we're trying to discuss in this slide. So let's move to the next. We also found when you will also need to consider a low temperature environment here. It's very important. So when the system outside, right, we know it's encounter extreme low temperature environment. So we would like to propose, I think we propose a special mechanism here is for extreme environment. And the idea here is to implement a heating module at the bottom of the system. So when the environment temperature is below to 0 degree and normally system will power off, the heating module should be turned on. And after the heating module run a certain amount of time, the sensor shows the liquid temperature goes above 0 degree, and the system should be able to power on. So the temperature the temperature mechanism will kick off to ensure the liquid temperature won't below to 0 degree during the operation. And we also have system sensors that which can monitor liquid temperature, and also it will activate heat module before liquid temperature drop right below 0 degree. So this is what we're trying to talk about here. And let's move to the next. The next is give you an idea of the different view of system architecture, and this is actually a real engineering sample. We'll just put it in the diagram here. So it's functional, and it's an early engineering sample. It's currently is available. All right, the next. We will talk about a little. We'll share about the system simulation overview. So in order to verify the feasibility of the prototype, and the fans are designed, you know, we also have a fan design inside the system to increase the flow field disturbance and to make effect of uniform temperature field. So we can read this simulation result shows that the uniform of the temperature field inside the system it is still sufficient. And the next will be our validation result to share with everyone here. So the result of the test that currently we can apply in an ambient temperature of minus 25 degree to 45 degree. Then again, we still need to continue focus on more high power key components to make our support temperature range bigger. So for example, GPU in a higher temperature environment. So therefore the next step, system validation will focusing on the thermal improvement on that part. And we will also continue to test the 55 degree. All right, so let's move on to the next one. And here is the engineering practice key learnings from our day one, and we would like to talk about and probably get some feedback from you. So for the solution where immersion is cooling, right, we found the design of the heat sink will also be readjusted. It's during our learning, under the action of thermal buoyancy, the thickness of the heat and the flow boundary layer need to be increased because the liquid is viscous. So that's what we found. And the main goal of the heat sink design here, we think, is need to be reduced the boundary layer interface, which will reduce the pressure drop and increase the flow rate to improve the overall heat transfer efficiency. So according to our thermal test result up to today, the optimal feed pitch we think should be between 1.69 to 2.5 millimeter. And with our first select liquid. All right, and so that is pretty much we would like to share today. And also the last one here, we will try to we will continue to contribute, and we welcome anyone who interested to collaborate with us, and we will continue to work with the work group in this committee. And continue to share our engineering practice and our future learnings as well. So I think that's all I have, and thank you. So any questions?
Yeah, there is one question that came in. Carrie, what is the maximum power that can be included in that box to remain fully passive? And at what point a pump and a fan will be necessary?
All right, I think if Levin is in the air, is on the air, I think I'll let Levin
So
to
Levin,
answer that.
if you can unmute and answer, that would be great. Levin, can you unmute?
So in the meantime, can I stop sharing? Okay, Levin, you go ahead.
Okay, can you repeat the question?
Yeah, the question is, what is the maximum power that can be included in that box to remain fully passive? And at what point is a pump and a fan necessary?
For the system, we will use the lateral friction. So actually, in the room we don't need the fan, but if the system is overheat, we will have the fan to turn on, right?
Okay, I'm not sure if that addressed the question, but maybe what you could do, Levin, is go into the FN virtual platform and answer it directly. I think that they would really appreciate